I have created a small video, नहीं बहुत बड़ा video actually, that is 49 minutes something, where I have explained some data science related questions. बेसिकली क्या हुआ था कि इंटरव्यू में ऐसे क्वेश्चंस पूछे जाते हैं, तो बोल के मुझे असाइनमेंट्स मिला था कि अपलोड अ वीडियो वाइल एक्सप्लेनिंग दिस क्वेश्चंस। तो सोचा कि वीडियो बना ही लेते हैं, एंड साथ ही आते जाते किसी डेटा साइंस एंथुसियास्ट का भला होगा, इसलिए वीडियो बना के मैं अपलोड कर रहा हूँ। इट्स नॉट लाइक 100% सही है या पूरा अच्छे से प्रिपेयर करके बना है, क्योंकि इट्स नॉट माई पार्ट टाइम जॉब, नॉट रैदर फुल टाइम जॉब। वैसे ही टास्क मिला था बोल के डाल दिया, बट स्टिल इन 49 मिनट्स यू विल गेट सम। अगर आपका मतलब डेटा साइंस में बहुत ज़्यादा इंटरेस्ट है तो फिर डेफिनेटली ये सारे क्वेश्चंस को देखिए, एंड या श्योर यू विल लाइक इट। एंजॉय। Yeah, good morning everyone. Uh, Today I'm gonna discuss most common asked questions in data science interviews. So, starting with the first question, like what are hyperparameters? Give some examples. What is hyperparameter term? So basically, hyperparameter is not like the common parameter which we see in a linear regression. Like after the linear regression, applying the linear regression, when the model gives an equation of a model where we can see that the parameters are there, beta 1, beta 2, etc. So hyperparameters are not like that, which is not learned by the model actually, you can say. uh, Hyperparameters are set by the users, like you can say that it is set by the data scientist, whoever performed the model. uh, what they do is like they control the behavior of the model. Like for example, uh, in a neural network, we have seen that the neural network may consist of many nodes, layers, and that is not defined, right? Learning rate, batch size. So these are all not defined. Like we can have as many as we want. So these are the hyperparameters which basically don't have any fixed numbers, like which which affect the learning, right? Learning of the model. So if we increase the number of layers of, or if we increase the learning rate, or if we increase the batch size, so definitely it's gonna have an impact on our model learning. So these are the example of hyperparameters. And talking about what is hyperparameter tuning, it's like an hyperparameter tuning is a process in where we're trying to find the optimal values for the hyperparameters. As we take in the example of a neural network, so their number of layers, the nodes, and the learning rate, batch size, all these are the hyperparameters. So as to create a good model, like you can say that model uh, which is which perform good on a test set or validation set. So to have that, we may need to find the optimal parameters for those hyperparameters. So this process is basically known as hyperparameter tuning. So moving on to the second question, how would you evaluate an unsupervised learning project? So basically, we have evaluation metrics like Slough score, uh, elbow method, purity and entropy, Kalinsky-Herzberg index, Davis-Baldwin index. There are some others as Rand and Jagged index. So we'll talk about Silhouette score. Basically, Silhouette score measures the similarity of each data point assigned to a cluster to compared to the other clusters. So if we see its formula, Silhouette score, that is bi minus ai divided by max of bi comma ai, where basically bi is the nearest cluster average of the nearest cluster distance, and ai is the average of intercluster distance, like the distance for a data point, and the distance from a data point to the other points which are in the same cluster, intra-cluster distance. And so I'm saying it again that Silhouette score formula is bi minus ai divided by max of bi comma ai. So we can notice that if the max of bi comma ai will always give an positive value. So it depends upon the sign of the Silhouette score, the sign of the score of the Silhouette score. It depends upon the bi minus ai. Uh, Actually, Silhouette score ranges between -1 to 1. So what happens is like if bi is greater than ai, that means for a data point, if its distance, its average distance to the nearest cluster is greater than like average distance of the intra-cluster members. So it is positive, right? Bi is greater than ai. That basically means bi minus ai is positive. So the whole result will be positive. Now, what happens is like when bi is smaller than ai, like when the average distance of a point to average distance of a point to the nearest cluster is lower than the average distance of a point from its intra-cluster members. So when bi is smaller than ai, so basically it means bi minus ai is going to give a negative result, right? So negative divided by positive, that basically implies that Silhouette score will be negative. So what practically it means is like for a negative value, the data point which we are trying to cluster, it may happen that it may be clustered to a wrong cluster actually. So that's why its average nearest distance is lower than the average nearest distance of its intra cluster. Because ideally what would happen, like ideally we want that for any cluster, if its member, if any data point it is member, so the average distance of its intra cluster should be minimum, like should be lower than the average distance of its nearest cluster, right? So that's why Silhouette score, the higher value of the Silhouette score indicates that the object is well matched to its own cluster and poorly matched with the neighbor cluster. So that basically means it is a compact clustering, right? And while a lower value of Silhouette score, which says that the data point may be clustered to a wrong cluster. Now we can talk about Rand and Jagged index. So basically, Rand and Jagged index are a bit different from Silhouette score in a sense. Like Silhouette score doesn't require the actual label of the class, while Rand and Jagged index need the actual label of the class. So this is why Rand and Jagged index may be termed, may be used in a class like supervised learning, like where we know our actual levels. And Silhouette score is good when we are not knowing the actual levels. Well, Rand and Jagged index, the range of the Rand and Jagged index is also between 0 to 1, and 1 indicating it's a the clusters are formed in a very nice way, and similarly for the Jagged. Now, moving to the third question. Yeah, the third question is if you move the classification threshold to zero point 0.3 to zero point 0.5, will the precision recall increase or decrease, and why? So, what I think is yes, the classification threshold, when we are like changing the classification threshold 0.3 to zero point 0.5, I think there is a change in the precision and recall. Uh, we can we can visualize it through an example. Like what we know is like precision formula is TP true positive divided by true positive plus false positive, right? Now we will take an example. Suppose 0.4. Suppose any data point which is after that is having an probability value 0.4 in output node. So when the previous threshold value was 0.3, that value, that data point 0.4, which is basically greater than 0.3, so it is classified as a positive. Suppose it is actually negative. So that comes under false negative. So it will increase the false positive value when the classification threshold was old, like 0.3. But when we are changing it to 0.5, what's happening is like that data point which is having a probability value 0.4, it's now less than 0.5. So it is classified as negative, and it is actually negative. So that's why it comes under true negative. So one value from false negative is getting lower. So basically, what's happening in a precision, it's like TP divided by TP plus FP. So FP value is getting reduced. So uh, sorry for that. So the precision value, that is TP divided by TP plus FP, will definitely increase because the FP value is getting lower, right? So similarly, there will be a change in recall. Coming to the next question, that is, what is the difference between test set and a validation set? And why validation set is required? So basically, the difference between the validation set and test set is based on their role play in a development process. Like the validation set is used to evaluate the performance of the model during the development process. And whatever we need to make decisions, like whatever we need to make adjustments on the hyperparameters that may be used in a model. So whatever changes that may be required is done using the validation set, and the test set is keep unseen, like it is not used in during the validation set. It is separate from a validation set, you can say. And after like evaluating the model on a validation set, we finally test our data, test our model in the test set. So test set is basically the unseen data. And talking about why validation set is required, it's basically required for like to ensure the good generalization of on a new data. Like we cannot say like if a model is performing good on a validation set, so we cannot say that it will definitely perform good on like new data. Okay, so for that we have to generalize our data. That's what generalization mean in machine learning. So by using a separate like validation set, that is a test set. So by using a test set, we can like finally make adjustment to our model. improve its generalization process performance. Coming to the fifth question, how to find the right threshold for clustering problem. There are several ways like precision recall curve, AUC ROC curve, then cost-based analysis, grid search. So these are the there are other ways too. So we are basically going to discuss on precision recall, where precision recall curve is a useful tool for finding the optimal threshold. What it does, it plots the recall values against the different threshold values. So we choose uh, we choose the threshold which maximizes the F1 score. F1 score, it is the basically harmonic mean of precision and recall. So we'll choose the threshold value which will maximize the F1 score. Uh, Now ASV RSV curve, the concept is here that the ROC curve plots the TPR against the FPR, like true. TPR is the true positive rate and FPR is the false positive rate. So here we're gonna choose the threshold which maximizes the area under the curve, AUC AUC value. So again, the choice of like we cannot say that we will choose like threshold which maximizes the F1 score or which maximizes the area under curve. It may depends upon the uh, problem statement. Like we may want, we may agree to the slightly lower precision value, and but we want a good recall value. For us, it is okay to have a like slightly lower precision value, but we actually want, like we mainly focus on a higher recall values. It may happens like in some problem statement, and it's vice versa. Like we may want a higher precision value and a lower slightly a slightly lower recall value may be acceptable. So that's okay. So it depends upon the problem statement. Coming to the sixth question, explain some regulation techniques in brief. So we have regulation technique as lasso, reach, plastic net, etc. And what L1 regulation is also known as lasso regulation, lasso regularization, where it adds the penalty term in the loss function uh, by taking the absolute value of the weights. So what it does, it like it have this method encourages the model to have sparse weights, meanings that some of the weight can be exactly zero, right? So when we are like optimizing this loss function, updated loss function, that is a previous loss function plus this L1 penalty term. So now what will happen? It's like it may like directly squeeze the squeeze those parameters to exactly zero. So it will make it will squeeze only those like parameters to zero which are like less relevant. So that's why it is it can be like this technique can be useful for feature extraction, like feature selection and reducing the irrelevant features. So in this, the lambda is the like hyperparameter which is uh, set in this lasso regularization. So the lambda controls the like effect of the strength of the regularization. So if we increase the value of lambda, that is basically means we are increasing the strength of the regularization. So it helps in reducing the complexity of the model. So we can say that it will decrease the variance and increase the bias. While when we decrease the value of lambda, what happen is like in it it decreases the strength of the regularization. So that's why it makes uh, like that's why there is an increase in variance and decrease in bias. So another regulation technique, that is L2, which is also known as ridge technique. So in L2, it is slightly different from L1. Just when we take the absolute value of the weights, here we are going to take the square value of the weights. So the rest of the process are same, like the optimization process and the loss function. So these are same, and but there is slightly a difference, that is the from L1, that is we take the square of the weights, and this method, as a like as we are taking the square of the weight, so that's why it not directly squeezes the irrelevant features to exactly to zero, right? So that is one difference from L1 technique. So this technique is also useful for reducing the impact of irrelevant features, and it improves the generalization process of the model. So when we have overfitting problem, so it can be used. And there is another regulation technique, that is elastic net, which basically uses both L1 and L2 regulation technique. Here we have two parameters, two hyperparameters. You can see it's alpha or beta, maybe. So alpha, which controls the L1 strength of the L1, and beta, which controls the L strength of the L2 regulation here. So elastic net is just a like combination of both. And there is something called as a dropout regulation and early stopping. These are related to deep learning actually. Uh, what happens in a dropout is dropout in a deep neural network. We randomly select a fraction of a fraction of our neurons, and those are set to the those are like not passed to the another layer, like the while like they are just dropped out. So it helps it this technique helps in reducing the overfitting. Like in every layer, it is not trying to learn every parameters. So what will happen if we learn every parameters in every neuron? It's that we will maximum of the time we will get overfitting problem. So that's why we randomly select some of the data, like some of the set in a layer, and drop those sets. And early stopping is also one technique which prevent the overfitting in a deep neural network. Another question, the next question is explain the bagging and boost. Mm, Seventh question, that is explain bagging and boosting. So bagging and boosting are the two ensemble techniques in machine learning. So ensemble technique is something like which combine the models to enhance the performance of the overall model, like overall to enhance the overall performance of the model. So in bagging, which is basically a bootstrap aggregation. So as the name suggests that it bags. So we create several bags using in bagging techniques, and bags are basically the that bags are usually the multiple independent models which basically trained on a random subsets of the training data, and that random subsets are basically chosen from the training data only with replacement. And every time that individual model gives the output, like we stored that output, and for giving an actual output, like overall output, we combine all the output of those independent models. So the overall the overall output is given using all the outputs of the individual model. So in this way, like bagging helps to like enhance the performance of the machine learning model. It also helps in reducing the overfitting and increasing the stability of the model. As we know that we are creating several bags of a model which are like running on a subset of the training data set. So what happened? It has what will be the effect of with respect to variance? So uh, we can see that by having a multiple models on a like different subsets, not exactly different subset in like every time, as we are like creating a sample with replacement, so there may be chance that the same data is involving in another model also. So that's why we are reducing the variance here. Now another thing that is boosting. So boosting is also an ensemble technique which involves the training of the multiple weak model. So yeah, there is one more difference between bagging and boosting. Is like bagging works parallelly, right? And boosting is sequentially. So what it means by parallelly and sequentially is like in bagging we are parallelly creating the models, and all those models are performing, and we are uh, storing its output to predict the final output. That's happening in a parallel, right? In boosting, it's sequential. Like first train the we first train the model with like multiple weak models. So first weak model is performed, and whatever the error arises, the next model is fitted in a such a way that the to reduce those errors. Like the main aim is to like regress those errors in the next like for creating the next model. So it is sequential. So boosting improves the performance of the model by reducing the bias. So we are seeing that in every iteration, what happened in the first iteration, the base model was created. So that is very big. Okay. Now, whatever the output of the base model is, uh, we calculate the error, and that error is now our target. Okay. So the next model which is built, that has the target to uh, regress those like errors. Then again, uh, we will have the output from those like the second model, and we will again calculate the error, and then again our target will be the like error 2 that is calculated using model 2. So this is how like we are getting close to the actual value. So it is reducing the bias. Okay, coming to the next question, that is, what is the difference between Euclidean distance and yeah? So we know that Euclidean distance is the like straight distance. Actually, we can say that a straight line distance between 2 points. And if you are calculating Manhattan distance between those 2 points, it will calculate it the distance using right angles. So the distance that is measured along the axis using right angles. It basically means like zigzag shape, right? In mathematically, we can say that it is a like sum of the absolute differences of the coordinates. So coming to the next question, that is explaining the functioning of K-NN algorithm and why it is referred to as a lazy. So, talking about the functioning of K-NN algorithm. So, K-NN is a supervised machine learning algorithm, which is a very basic machine learning algorithm. This algorithm works like by finding the k nearest neighbor. Like k is the number of integers here. Basically, it denotes the number of neighbors. So this algorithm works by finding the k nearest neighbor to a query point based on a some distance metric like Euclidean distance. It can be Manhattan, anything. So based on the distance, it finds the k k nearest neighbors, and then it assigns the label to that query point based on the majority of that those neighbors. Like for example, if we are like if we want to, it's just like a majority voting system. Yeah. So talking about why it is referred to as a lazy learner, because in Canaan there is no actual learning is happening, right? Because this model is not learning from the training data. Instead, it is using the distances, like stored distances, to compare to compare with the query point. Like if a query point comes to a Canaan algorithm, it just compares its distance to all other points and select the k nearest members to it, and uh, based on their class labels, majority of the class labels, it also predict the label of that query point. So you can see that there is no actual learning is happening. That's why it is called as lazy learning. Also, uh, it is computationally high when it comes to like test phase rather than training phase, because in training phase there is no training actual, no actual training is happening. So that's why during the training phase it is very computationally very cheap. And coming to the next question, like what do you mean by the model explainability, and how would you introduce explainability to a black box model? So, model explainability refers to the ability to understand and interpret how the machine learning model makes predictions. Like, uh, if a model is there, and there are different scenarios where model explainability can be important. Like, suppose you are a credit, like suppose you are a company which is giving credit to someone based on the credit score, and there are several features are there, right? And you want whenever you want to, like suppose you want to classify that whether your customer is eligible to get the loan or not. So you want, like when you build a model, you want that there should be model explainability, so that you can when you classify a user is like not getting a loan, so you can like uh, say to the user, mention that user that you have lower this feature, you have lower this feature, or you have higher this feature. So it should be interpretable. The model should be interpretable so that we can like give reasons to that judgment, right? So that's why model explainability is also important. And talking about how do you introduce the model explainability to a black box model. So black box model is something which is like which have we can say zero model explainability, not zero, actually it's an like no model explainability, can say. Like most of the deep learning models are black box, and there are like several models. We can take an example of linear regression, which is a white box model, which is not a black box, we can say, which is easily interpretable. And most of the deep learning models are black box. So here we can introduce the explainability to a black box model, but that should be like a random forest and all, not like completely black box type. So in some extent to a black box, it's okay. So for those to introduce the explainability, we can use a SHAP, that is Shapley additive explanation. We have a LIME, that is local interpretable model agnostic explanation. There is a EL, something called as ELI 5. Explain me like I am 5. That is actually its full form. And yeah, that though this thing we can use for the explainability for a black box model. Now, coming to the next question, how do we evaluate a regression problem? And what is the difference between R2 and adjusted? So there are several methods to use to like evaluate the like regression problem. We can use MSC, which is the mean squared error. Then we can use RMSC value. Then we can also use F1 square, F1 statistics. Then these are the methods that we can use basically, and like mean squared error and like RMSE, there is one difference, like it's root mean square. RMSE is the root of the mean squared error. That's just one difference. And talking about the difference between talking about the difference between R2 and adjusted R2, like we can say that adjusted R square is a modification of the R square, and it was introduced because like when we have a MLR problem, multiple linear regression problem. So the number of the number of independent features when increased from one to more than one, then what happen is like the R square value is biased. Okay, so the more we increase the independent variable, the R2, the like R square value is biased to the number of increase uh, in the independent, if the number of independent features are increasing, so R2 value may also be increasing. So that's why we have something called as adjusted R square, which is a, here you can see the formula also, that is 1 minus R square into n minus 1 into divided by n minus p minus 1. Okay, so in case of MLR, multiple linear regression, we mainly focus on the adjusted R square values. Although in a practical, that is very slightly different. There is a very slight difference. So sometimes it's negotiable, but it's mainly preferred to focus on the adjusted R square in case of MLR. Yeah, coming to the next question, like what is the difference between deep learning and machine learning? So there are basically many differences in deep learning and machine learning. Many people think as it is like many people have confusion related to deep learning and machine learning. So deep learning algorithms are basically like, I will try to explain in some points. So deep learning algorithms are typically complex models which are used for the complex problem statement. If you have a complex problem statement, then you can use deep learning for that. And if you have like simple, not too much complicated problem statement, then you should try uh, like running machine learning model on that. If it is not working, then you can go with the deep learning. So second point is like deep learning models are mostly black box model. And deep learning models basically mostly requires a large number of data sets. Yeah, to work good. Basically, it doesn't work good on a smaller data set. And deep learning feature, it can automatically learn features. There is no feature engineering part in the deep learning. Right? In machine learning, the algorithms are simple, and most of the models are white box type. Like it have the model explainability, and generally doesn't require too much large data set. When you have a small data set, then you can go with the machine learning model. And it also and here we have to here we have feature engineering part, and like there is no automatic feature engineering here. So we need to like extract the features and then give it to the ML model. So the next question, what is the difference between gradient boosting and ADA boost? So gradient boosting and ADA boosting, both are the boosting techniques only, but they differ in a way during the iterative process. So in ADA boost, that is an adaptive boosting technique. So the changes happens in the sample distribution by modifying their weights attached to the each instance. Okay, so it increases the weight of the wrongly predicted instance and decrease the ones of the correctly predicted instance. Okay, like in every instance, like in every iteration, when we like when we got to know that okay, these are the like these are the parameter these are the data points which are performing good, like they are having giving the actual result. So it what adabos do is like it reduce their weights. It says that okay, you don't need to learn more, just take rest, and I will focus on those those data points which are like giving bad results. Okay, so similarly this process go on. While in a gradient boosting, what happens is you can see that in gradient boosting is also a boosting technique. It doesn't modify this sample distribution. It you can say that when a weak model, when a weak learner model is that is a base model for the first time. Uh, so when a weak learner model is a is trained on the entire data set, then the residual errors are calculated. Like we say it has a pseudo residuals here. So basically the residuals that are calculated using the previous like using the output of the previous weak learner model, these are pseudo residuals. So the next model, that is weak learner model, is built. They have the target to reduce this pseudo residuals to make the stronger model, like a stronger learner. Okay, so several weak learner model are like combined to make a stronger learner model. So this is the concept of the gradient boosting here. And coming to the next question, that is what is vanishing and exploding gradient? Yeah, vanishing gradient problem and exploding gradient problem. These are the two problems. First, vanishing gradient problem. What happens is like in vanishing gradient problem, the gradients become very large. Sorry, very small. Uh, During the back propagation process, when the derivatives are too small, right? Like where we have a neural network, suppose, and we have several layers. Okay, so when the errors are back propagated, okay, So the derivatives are calculated. So for the first time, suppose we have a very less derivative. It's between 0 and 1, suppose. So to get the error at the input node, we have to multiply the error that we have calculated from the output node and take the derivative of that, and then multiply with the rest other derivative of the previous models. So while multiplying those derivatives, if the derivatives are too small, then uh, that's just a mathematical concept. Like if you multiply 0.1 with 0.3, the result will become smaller and even smaller. So if we are continuously multiplying with a small number, then there is the final gradient that we need to update, right? The weight updation, where we have to increase with the gradient that we have calculated. So the gradient become very small. So that's why the weight updation is very slow. Okay, so that makes very slow convergence to a model. Okay, and for exploding gradient problem, it's just opposite of the vanishing gradient problem. It occurs when the gradients become very large. So it is also a same problem when suppose the we are calculating gradient on the input side. So if the gradient at the error side is larger, then it is multiplied with a gradient at previous layer. Suppose it is also larger. So when we are like larger, it basically means one greater than one. So if we multiply two with three, then it will increase the number, right? Then then again gonna we are multiply with a larger number. So it will basically raise that number to a very large quantity. So if we are using a very like suppose uh, a large, you can say a large number of layers. So in that case, the vanishing like in that case, the gradient that we calculate during one iteration at the input node will be very higher. Okay, so that's why the weight updation will be like very high. Okay, so that's why it is unstable. We can say it's unstable because where we where we need to change the weight very slight, like very little bit, but our gradient is due to like exploding gradient problem. It like the gradient become very high and the weight updation become very high, so it is unstable. It is unable to converge, like not unable, it is very unstable convergence, right? Coming to the next question, what is the difference between ANN and CNN, and why CNN is used for image processing? Yeah. So the difference between ANN and CNN can be given in 2 3 points, like based on input structure. So like ANN can take uh, unstructured or structured type of data, but CNN is designed to work on a grid-like data, like such as images, videos, etc. And another difference would be like based on architecture. Like ANN, we can see that it consists of input layers, hidden layers, and there is output layer. So this is the structure. This is the architecture of the basic NN model. While CNN is consists of a convolutional layer, then there is a pooling layer, and then comes the fully connected layer. So from the fully connected layer, it behaves like an ANN. But before the fully connected layers, there in CNN there are several techniques such as the convolutional layer, pooling layer. These are the things. Now, coming to the question like why CNN is used for the image processing. So that is basically for its, like, we know that the CNN is having convolutional layer and pooling layer. So this can be useful for extracting the features from the images. So uh, like extracting the features, any kind of feature like edge detection, then it can be finding the context, texture of the image, etc. So these are the several features which are very essential during for the image processing. So that is why CNN is used. So thank you for listening this